Welcome to Train Signal. I'm Chris Bryant, CCIE number 12933, and this is the Ethernet behavior and standards video. And we're also going to have some VLAN implementation. A VLAN is a virtual LAN as opposed to the physical local area networks that you're certainly familiar with by this time. And we're going to start this video with a discussion of what collisions are and what CSMA CD is. And that helps us lower the number of collisions when hosts are sharing a segment. That's why I put in a shared segment environment there. After that, we're going to compare collision domains and broadcast domains. This is something that regularly gets a little confused by exam candidates, and we're going to clear that confusion up totally in this video, because a collision domain and a broadcast domain are two totally separate things. And you'll know how to define those and how to chop them up, so to speak, into smaller parts through the use of virtual LANs. And if you have to get used to something in networking here, if you've not worked with something like a virtual LAN or a virtual link in OSPF, which is a routing protocol, you're going to work with some virtual interfaces throughout your career. You're going to work with virtual local area networks. And you're going to work with virtual routers as you continue your career and if you go on the WAN side. So you have to get used to the fact that not everything we use in networking is physical. Sometimes we're going to make some logical divisions in a physical network, and that's what a virtual LAN is all about. You'll see what I'm talking about when we get there. We're going to tie that into a discussion of layer 3 switches. And your networking theory states that switches work at layer 2 and routers work at layer 3 and the OSI model, and that's it. But in today's networks, that's not it. And your Network Plus exam will be very straightforward. There aren't going to be any questions there trying to trick you between a regular switch and a layer 3 switch. But to be totally educated about switches, you've got to know that layer 3 switches exist. So I'm going to tell you about them for just a few minutes there and how we can use those. Then we're going to look at router on a stick. And it's a great name for a little trick we can do with certain kinds of routers. And I did not come up with that name, but I wish I had. Router on a stick. I always love that one. We're going to wrap it up with a look at the IEEE Ethernet standards, because we no longer just have Ethernet. We've got Ethernet, we've got fast Ethernet, we have wireless Ethernet, which we'll talk about later in the course. We have gigabit Ethernet, we have 10 gigabit Ethernet. Now, you don't have to have worked with all of these to pass Network Plus, but you need to know the standard numbers, and those are the kinds of things that cert exams really like asking about, so we're going to cover those in detail as well. So we're going to start this discussion of CSMA CD by talking about what the heck it is in the first place. And this really comes into use on a bus topology, which we're going to look at here in a moment. You already know what that is when we've got multiple hosts sharing a segment. Well, when hosts are sharing a segment, their data is subject to a collision. And here's our old friend, the bus topology. And what we have to be conscious of is that host A and host E, if they send data at the same time, it's going to collide. And just as automobiles can become unusable after an auto crash or an auto collision, when data collides, both signals become unusable. All the data is unusable. So we want to avoid that in the first place. But what we also want to avoid is a situation where host A and host E both say, oh, okay, well, I think my data was just in a collision, so I better send it again. And then they send again at the exact same millisecond. And then we just start all over again. The data is unusable again. So there are two things we want to avoid. We want to reduce the number of collisions whenever possible. We can't eradicate them in a network, but we can really lower their number. And also, we want to make sure that if there is a collision on a segment such as we see here, that it doesn't just keep happening and keep happening and keep happening. And what we've got with Ethernet is a set of rules called CSMA CD, and that is carrier sense multiple access with collision detection. And that is quite a mouthful, which makes you glad that we call it CSMA CD. But one thing, I want you to get in the habit of this. I know that I am throwing a lot of protocols and a lot of different things, a lot of different terms at you that you may or may not have heard before. It's hard to remember what all this stuff does. But what I want you to remember when it comes to exam day or a job interview or anything else is that if you know what the acronym stands for, you can pretty much come up with the meaning of it. And sometimes we use the acronym so often that you forget what they actually stand for. It's like when we talked about ARP. And you might think, well, what does ARP do again? Well, it's an address resolution protocol. It gives you a little hint as to what's going on. If we break the term CSMA CD down into its smaller parts, we can see a lot of what's actually going on. Because the carrier sense part means hosts are listening to the wire before sending. And what do I mean by listening to the wire? Well, with a bus topology, they're listening to see if anybody else is sending right now. Multiple access refers to the behavior that more than one host is doing this. All the hosts on that segment, it's multiple access. We've got more than one device, and they're all performing this action. In collision detection, the name is the recipe. It's a host's ability to detect that their data has been involved in a collision. So now we know what CSMA CD is, but let's look at the details of it. Let's go through a scenario on that shared segment where A and E, host A and E that is, are both getting ready to send data out onto a shared segment. The first rule of CSMA CD, and actually the very first part of that, CS, carrier sense, is where the hosts are going to listen to the wire or the physical segment before sending. It's usually referred to as listening to the wire. So let's walk through this step by step. We have host A, we have host E, and host A wants to transmit data. Well, it's not just going to start sending it. The first thing it does under the CSMA CD rules is listening to the wire. And what it's listening for is another host's data already on the wire. So host A will listen to the wire, and if there is an electrical signal going across that wire, because this is the physical layer and that's what our data is, it's all ones and zeros. If that host detects a signal on the wire, it's not going to send anything. It's going to wait. Now when there is no other host on the segment transmitting data, host A will go ahead and start transmitting. Now CSMA CD is very good at helping us to avoid collisions, but it's not perfect because collisions are going to happen sooner or later, especially in a shared segment. Now let's say again that host A and host E both have data to send, and they both listen to the wire at the same time. We've got a quiet network. And host A and host E at the exact same millisecond, and this happens more often than you would think. It's not like hitting the lottery. Host A and host E both say, I want to send data right now. And they both listen to the wire at the same time, and they hear nothing. And then they both say, okay, I'm going to go ahead and send my data onto the wire, and they both send it at the same time. They both start transmitting, and that's when we have a collision. Their data is literally going to collide. Now, what's actually happening there is when a collision occurs, the voltage of the signal actually changes, which results in what we refer to as noise. There's always some kind of signal on the wire. I mean, the data is a signal itself. But the term noise is used to describe the change in the signal when data collides with other data. Now, we talked about collision detection and how hosts know that their data has been in a collision. Well, when that noise occurs, when that collision occurs and we get that noise, that change in the voltage, the sending hosts are going to hear that. Everybody on the segment's going to hear it, and they basically say, uh-oh, that was my data. If I just sent data out onto the wire and I almost immediately heard a collision, then that must have been my data. So the sending hosts are going to hear that noise, and since they just sent data out there, they know their data has been involved in a collision. Well, now we really need to make sure two things get done. First, we've got to make sure that the other hosts are warned not to send data until this collision is cleared up. So that's one thing we got to do. The other thing is that the sending hosts have got to retransmit their data because it's now useless. It's been rendered useless by a collision, but not at the same time. Because what's going to happen if that happens? Another collision is going to occur. So we need to have two things taken care of. The other hosts have got to be told somehow, hey, don't send any data out, don't even start the process because there's been a collision. And now A and host E both have to send out their data again, but we can't let that happen at the same time. Luckily for us, CSMA CD is going to take care of both of those situations. The first thing that's going to happen is that the hosts that sent the data that was involved in the collision, they are now going to generate a jam signal. And that's going to be heard by all other hosts on the segment. And that jam signal indicates to the other hosts, don't send anything. There's a problem on the wire. So the jam signal goes out, and the other hosts aren't going to send any data, so now half the battle is won. But now what we've got to do is make sure that host A and host E do not retransmit at the exact same time. Because if they do, obviously we're going to have another collision. Well, to avoid retransmission at the exact same time, both hosts will invoke or just start a random timer. It's sometimes called a back-off timer. And that tells the host how long it should wait before listening to the wire again. Now again, that's a random timer. That's not something that you and I as network admins or router engineers could go in and fix. So what happens is that this is measured in milliseconds. So the chances of host A and host E waiting exactly the same number of milliseconds before listening to the wire again is scant at best. And please note, very important detail here of CSMA CD is that when that random timer expires, they don't just send the data out. The random timer is defining how long it is before they start the entire process of listening to the wire again. It's a very important little detail about CSMA CD. So that's the basic operation of it. The hosts are always going to listen to the wire first. And if they don't hear anything, then they'll transmit data. If two hosts on a shared segment happen to do that at the exact same moment, their data collides, it becomes unusable. They're going to both generate a jam signal telling the other host, don't send anything, and then they're going to start a random timer in milliseconds, and when that expires, then they start the entire process again. So when collisions do occur, the chance of another collision occurring by the same two hosts is very, very slim. Now, regardless of how long you've been around networking, you've probably heard the term domain. And that term gets applied in a lot of different situations. And that includes collision domain and broadcast domain. And right now we're going to look just strictly at collision domain. A collision domain is simply the area in which a collision can occur. So the segment that we're looking at right now, that is one big collision domain, because any data that one of those hosts sends out is subject to colliding with data sent out by another one. Now again, collisions are not the end of the world. I mean, they're actually normal. When you go onto a router, say, and you look at the number of collisions on a segment, you're going to see something. You're not going to see zero. You're going to see some data collisions out there. But we really want to avoid them whenever possible. And this is another reason why bus topologies are not scalable. Remember, we talked about that in that particular video, where we said, a problem with bus topologies is they don't handle growth very well. They're not scalable. Well, the more hosts we put on a shared segment, the larger the chance of data colliding. So shared Ethernet segments, they're not really set up for future network growth. We can add to them, but we probably don't want to. And a much more scalable solution is what we call a switched Ethernet environment. And that's going to look something like this. Now, of course, you recognize a switch by this point. Now, we could have hubs here, but the more realistic scenario that you see today has each host connected to its own little port on the switch. And this helps us out in another way, because every port on a switch is its own little collision domain. So in the example that we've got on the board right now, collisions between the 5 hosts cannot occur. Host A and host E can send data at the same time, and that data is not going to collide because they're not on shared segments anymore. They've got their own dedicated connection to the switch. And this, of course, remember what kind of topology this is? This is a star topology. And that's why you see them so often, because their data can't collide. It has no one to fight to get to the switch. They've got their own connections. So, you know, we've got a good news, bad news situation here, which you're probably already getting used to in networking. The good news is we have 5 collision domains where we have 1. And the first time you hear that, it sounds bad, but it's really good. You want as many collision domains as you can, because the more collision domains you have, the less chance of the collisions occurring you actually do have. The real bad news here at this point is that we have one big broadcast domain. So let's go back now and talk a bit about broadcast domains and what we can do on that switch to perhaps break those up a little bit. By default, a switch is going to forward a broadcast. And switches can have a lot of ports. We can have a 12-port switch, we can have an 80-port switch. And again, by default, when a device sends a broadcast frame to the switch receives it, the switch will send that broadcast frame out every single port except the one it came in on. So that means that by default, all hosts connected to a switch are in the same broadcast domain, because when one host sends a broadcast, every other host is going to get it. So that's a waste of bandwidth in and of itself, and we want to be careful, especially on our local area networks, not to make the assumption, and it sounds silly when you say it out loud, but occasionally network admins, they kind of run their networks like bandwidth is endless. And bandwidth is not endless, it's limited, and we don't want broadcasts taking up too much of our bandwidth. And you may think, well, you know, if you're sending, you know, an ARP request out or something like that, is that really going to take much bandwidth? Not by itself. And what we want to prevent, though, is what we call a broadcast storm, because broadcasts tend to result in even more broadcasts. There are routing protocols not covered on the Network Plus exam. I'm going to mention them to you later in the course. But there are routing protocols that use broadcasts to send routing updates. And these broadcasts tend to result in other devices sending more broadcasts as well. And if you pursue your CCNA and you go on from there as far as Cisco certifications go, you'll run into more and more and more situations where broadcasts beget more broadcasts. And you want to be careful about that. And right now, at this point in your career, start looking at that. You know, start examining your network, start examining things that you may put on your network 1 year from now, 2 years from now, and just say, you know, are the broadcasts for this going to cause an issue? Are they going to cause what we call a broadcast storm? And a broadcast storm is that situation where one device is sending a broadcast, all the hosts on the switch get it, and as a result of that broadcast, they send a broadcast of their own. Well, now you've got a lot of broadcasts flying around a switch. And what happens is it's a snowball effect. It doesn't happen all at one time. But this snowball effect ends up in what we call a broadcast storm. And I have seen this happen where broadcast storms can actually take a switch down, because they're going to take up all the bandwidth, they're going to take up all of the switch's CPU, all the processing power. It's going to be so busy handling broadcasts that the real data that the hosts are trying to exchange literally won't be able to get through. So that is a real danger. And more than likely, on your network or on any given network, there's no reason for every host to get every broadcast that is sent out. Because more than likely, only a few hosts on each switch really need to communicate with each other. You've got different departments, you've got different floors if you wanted to break it up by floors. But what we're going to do here is work with an 8-port switch, and we've got 3 hosts in a security department, another 3 hosts in the accounting department, and 2 more in the publishing department. Now we've got 8 PCs attached to a switch at this point, and I actually titled this picture VLAN 1 or Virtual LAN 1 because by default, again, all of these switches can, if they generate a broadcast, all the other hosts are going to get them because they're all actually in a virtual LAN at this point. They're actually in virtual LAN 1 if we were working with a Cisco switch. And people tend not to realize that. And we're going to talk about exactly what VLANs do in a moment. But again, by default, all of these hosts are in the same broadcast domain. If one generates a broadcast, everybody else is going to get it. And more than likely, we don't really want that. And we've got 3 different departments here, and perhaps they really don't need to communicate with each other. If one sends out a broadcast in accounting, say, if one of the accounting PCs sends a broadcast message, we only want the other accounting PCs to get it. And we can make that happen with a virtual LAN or a VLAN. And physically, these hosts that we're looking at here are all on the same LAN. They're all on the same local area network. But we can configure the switch to place them in different logical LANs, and that's what we mean by a virtual local area network. We're going to logically segment this network into smaller pieces. And the great thing about VLANs right off the bat is that when a switch is configured with multiple VLANs and the hosts are put into them, the switch will then forward a broadcast only to the hosts in the same VLAN as the host that originated it. So when we create VLANs, we're actually creating smaller broadcast domains. And the more broadcast domains we have, the less of the scope of the broadcast is, that is the range. Not everybody's going to get it. And logically, this is how we could divide this particular network. We could put the 2 publishing PCs in their own VLAN, put the 3 accounting PCs in their own VLAN, and put the 3 security PCs in their own VLAN. And there are different ways, there are different formats you could use, or different values, I should say, to assign VLAN membership. The most common is to place certain switch ports into a VLAN. But there are more advanced techniques. You could use the host MAC address to assign them to a certain VLAN. You could even use the network protocol that the hosts are using. And say if they're using protocol X, put them in VLAN 10. If they're using protocol Y, put them in VLAN 20. But in my experience, it is much more common to assign VLAN membership by switch port. You go on the actual switch itself and say, okay, this port, whoever connects to this port is in VLAN 10. Whoever connects to this port is in VLAN 20, and so forth. And the reason I numbered those here is that almost all switches are going to require you to assign a number to a VLAN when it's created. And you can name it after that, certainly, so that when you look at the switch, you say, okay, VLAN 10 is the publishing VLAN. Then you could do that. Now we've got another good news, bad news scenario. And this could be good, bad news or not. It just depends on your network. Now right now, we know that we have 3 separate broadcast domains. And the key here is that if one of those PCs in the security department sends a broadcast, only the other 2 PCs in that department are going to have it forwarded to them. So that takes a processing load off the switch. It also means that we have less bandwidth unnecessarily taken up by broadcasts that the other PCs may not need. The problem is that no other traffic is going to be able to go between VLANs either. By default, there will be no inter-VLAN traffic on the switch, period. So when we create our VLANs then, we've got to take into account, well, do we want these PCs to be able to send data to each other, period? And maybe you don't. one scenario used for VLANs beyond the broadcast domain is that you may have a secret department in your network. You may have a security department. You may have an accounting department. Some department that you don't even want the rest of the network to know that it exists. If you put them in their own VLAN, no one else will know they exist. And no one else will be able to communicate with them unless you do something about that. So occasionally that has happened. It's happened in my career. It may well happen in yours. You've got a department you just want to isolate from everyone else, and you can do that by putting them in their own VLAN. Now again, before we talk about how we can allow inter-VLAN traffic, and there are a couple of ways to do that, we're going to take a look at a practical example here of the VLAN theory that we just spoke about. And again, I want to reiterate, when we put virtual LANs into place, broadcast won't travel from one VLAN to another. That's good, but the bad news is no other traffic will either. By default, we're not going to have any inter-VLAN traffic at all. In the network that I'm about to call up on the window, I'm actually using Cisco routers to do this, to act as host devices. And right now I've got one where the Ethernet interface has an IP address of 172.12.1.2 with a 24-bit mask. The other has 172.12.1.3, 24-bit mask. If you're not too familiar with what that mask means or why I call that 24-bit, hang in there. That is coming later in the course. But I just want to put that up right now for completion's sake. And what we're going to do is see whether they can communicate right now and give you a little sneak preview as to how we do test if devices can communicate without trying to send data between the two. And then we're going to put them in different VLANs and see if they can or can't communicate. So we know the theory of VLANs, but now we're actually going to see it in place, see it in action. So let's bring those up, and I'll show you the IP addresses that I put on their Ethernet interfaces. And here's host A. I'll do a quick show config for you. And you can see right here, here's interface Ethernet 0, IP address of 172.12.1.2. And we're going to go over to host B. Do a quick show. And you see we've got an interface Ethernet 0, 172.12.1.3. And the command that we use, the basic command we use to test IP connectivity is called a ping. And you may or may not have used this before. So I'll go over a quick bit of theory here. We're going to look at it again closer in the troubleshooting section of this course. But a ping is your basic IP connectivity test. It's not going to show you the path between host A and host B. It's just going to say either we can communicate with that device or we can't. And what you do is simply type the word ping followed by the IP address of the device in question. And I hit enter. You could see 5 100-byte ICMP echoes. ICMP is the protocol that includes ping. And you see 5 exclamation points right here. We always want to see that. That is the best possible result, because that does mean that we have IP connectivity with that remote device. And we could go right over here to host A and put ping 172.12.1.3, and we have connectivity. You'd think that we wouldn't have to do that, but always test connectivity both ways if you can. And so right now, that's just like 2 PCs sitting on the same segment. And let's take a look as to why that is. This is the switch that's connecting them. And if we'll go back up here, let me do another command, because this is a show VLAN command on a Cisco switch. This is a 2950 switch. And you can see that all the ports over here are active, and they are in the default VLAN of VLAN 1. So right now there's absolutely no connectivity issue at all. They're in the same VLAN, they're on the same subnet, so there's no problem. But what if the VLANs were different? What if if host B was in another VLAN? Well, let's change that, and you'll see how we do that on a Cisco switch. Just a sneak preview for you. and then we'll test that VLAN theory that we were just talking about. We're now going to change the VLAN membership of host B and actually put it into another VLAN. And again, just a quick lesson on how to do this. I mentioned that we've got a couple of different methods we can use on a switch to change or assign VLAN membership. And the one we're going to do here is by port. And again, these are not commands you need to know for Network Plus. This is how you change VLAN membership or assign it on a Cisco router. Put in VLAN 3. And it created the VLAN for us because it didn't exist. So now, let's take a look at the VLAN situation on the switch. And you can see now that VLAN 3 has been created and port 03 has been assigned to that VLAN. And host B is connected to that port. So now the two devices that were just exchanging pings are in different VLANs. So let's take a look at that and see what happens. Okay, we're pinging 172.12.1.2, and just a minute ago we were able to send that ping through, and now we can't. And the reason we can't is because they're in different VLANs. Now, not only is any broadcast that host B sends out not going to reach host A, but no data, period, right now can reach host A. And the situation is going to be the same from the other side. And when you see 5 periods right here show up as a result of a ping, that is not good. And the 5th one times out. You see a success rate is 0%. So literally, we took 2 PCs, 2 host devices, that were able to ping each other a few minutes ago because they were in the same VLAN. There was no problem. But as soon as we put them in different VLANs, it was all over. So now we would have to get another device involved in order for these 2 hosts to communicate. Well, let's talk about what those are. When I mentioned that we need a device to allow inter-VLAN routing, used to be very simple. We would say, okay, you need a layer 3 device. And the only layer 3 device we deal with is a router. That's what works at the routing layer, or the network layer officially of the OSI model. It's not quite as simple anymore because the line between layer 2 and layer 3 in real-world networks is getting a little blurred. And you'll see what I mean in just a moment. But in the study materials and on exam questions and that kind of thing, when they're asking you about networking theory, which Network Plus is obviously going to be very heavy on, they do draw that line right there between layer 2 and layer 3, where layer 2 devices are switches and they switch, and layer 3 devices are routers and they route, and that's it. But in real-world networks, it's not like that. And what I'm going to show you here is not very complicated at all, but it's a device you need to know about, and it's called a layer 3 switch, or an L3 switch. This is not a switch that works exclusively at layer 3, but it is a switch that has routing capabilities. And these switches are getting more and more inexpensive as time goes on, as technologies usually do. And as small to mid-sized networks, especially say like schools, smaller offices, private offices, that kind of thing, but especially schools, I've noticed when they do a technology refresh, which is a fancy way of saying they buy new stuff. I'm in contact with quite a few school systems, and what they do when they do buy their new networking stuff, instead of getting a switch and a router at every school that points to the hub, they just buy a layer 3 switch. And that way, they can perform switching on most of the ports, but they can perform routing on the ports that they need to. And you can run a routing protocol on there with no problem. A Cisco layer 3 switch, you can run RIP, OSPF, EIGRP with no problem at all. And it really is a fantastic device. Now again, I want to reiterate the Network Plus exam, the CCNA exam, Microsoft exams, they're not going to try to trick you on this. if they say switch, or you read switch, say in one of my books or someone else's book or in network documentation, when you see the word switch, they mean a layer 2 switch. They mean a pure L2 switch. If you are documenting or writing about layer 3 switches, you're actually going to say L3 switch. So don't want you to get confused on that when you hear about it in a real world network or in a job interview and somebody talks about a layer 3 switch and you're thinking, well, wait a minute, I didn't know there was such a thing. There is such a thing. They're getting more and more popular. But again, on your cert exams, if they mention switch, they're talking about a pure layer 2 switch. If they want to ask you about a layer 3 switch, they're going to mention a model number or actually say L3 switch. I don't think you have to worry about that here on the Network Plus exam, but I do want you to know that they do exist because they're getting more and more popular, and if you haven't worked with one yet, you probably will one day. Now, the bad part about layer 3 switches is they tend to take away from a configuration that I love, the configuration of router on a stick. And actually, while I do enjoy configuring this because it's a little bit of a challenge, I just like saying the name. I think it's hilarious. Router on a stick. Well, what stick are we talking about here? Well, it's nowhere near as fun as it sounds. It's just the stick we're talking about is the connection between a switch and a router. And it's a single physical connection. We can connect a router directly to a switch to perform router on a stick. And the inter-VLAN traffic is going to be flowing up and back down that single cable. So one thing right off the bat, and this trips a lot of people up when they start with it, your router interface has got to be at least fast Ethernet. I don't think you're going to get many gig Ethernet ports that you can spare to run router on a stick. But if you did, you could do that. But you've got to have fast Ethernet at least. Some of the older router models that just have Ethernet ports, you can't use that for router on a stick because that interface has to be capable of simultaneous transmission and receiving of data. And a regular Ethernet port, of course, running at 10 meg, it's half duplex. And if you're not familiar with that term, we'll review it in a moment. But half duplex means you can send or receive, but you can't do them both at the same time. And that's the kind of port we have to have for router on a stick. Now, router on a stick, as I know here, is being used less and less because of layer 3 switches. Layer 3 switches are more efficient because if we use an L3 switch, the data never has to leave the switch. It can actually be routed on the switch. It makes things more efficient. But router on a stick is still effective for permitting inter-VLAN traffic. And physically, it's going to look just like this. If we introduced a router into the current network. Now, I took the VLAN boxes out for clarity's sake here. But what we could do is on the router, just to give you a little bit of detail here as to how you do it, on your fast Ethernet port, you configure what we call sub-interfaces. And those are simply a logical division of a physical interface. Again, earlier in the course, I told you you're going to have to get used to logical interfaces and logical links and that kind of thing. And that's what sub-interfaces are. They're logical interfaces. They do not physically exist, but we've configured them into the configuration of the router. And all you have to do is configure one sub-interface for each VLAN, give that sub-interface an IP address that resides in that VLAN, and do that, and you're really ready to go. There's a little additional coding depending on what vendor router you're using, but the configuration of it's actually pretty simple. The concept I really want you to grasp for right now is that to allow inter-VLAN traffic, we have got to have some kind of layer 3 device perform that routing. And in today's networks, we've got two choices: a router to perform router on a stick with, or a layer 3 switch, which means the traffic never has to leave that switch. Pretty sweet stuff. When you start working with layer 3 switches, it's like when you get wireless Ethernet at your home or at your office, and you use it for a day, and you just think, how did I ever live without this? And when you use a layer 3 switch, you're just thinking, wow, how did I ever get along without this? Great stuff. Just a quick review here of half duplex and full duplex before we talk about some Ethernet standards and maximum speeds. Half duplex, again, does not allow simultaneous sending and receiving of traffic, while full duplex does. You can set fast Ethernet ports for half duplex. I've never seen a good reason to do it, but you can do it. Here's a list of some Ethernet standards that I think would be a good idea for you to know, like the back of your hand for Network Plus. Because let's just be realistic here, especially with exams that are heavy on theory, as Network Plus is. If there's a list of stuff, I would know that list of stuff. It couldn't hurt a bit. So we're going to revisit some of these later when we talk about cable types in another video. But I want you to be really familiar with these particular standards I put up here. And just as a reminder, if you go Googling for any of these or using your favorite search engine, just put IEEE in there and then follow it with this, and you'll get some very technical documentation. Some of it's a little thick, some of it's a little dull, but you know, if you're having trouble sleeping, go out there and pull down some of that documentation. I've actually found, if you go to wikipedia.org and look up any of these, there's actually some pretty interesting reading there. And actually, I'll just I'll jot that out here. This is not a paid endorsement. It's going to put a little misspelling thing there, but we won't worry about that because I'm going to take it off here in a second. But wikipedia.org, if you've got a question about any kind of cable type or really a question about anything, especially in the technological area, there's some really good stuff out there. And I'm not saying that because I wrote it, because I didn't. But there's some excellent stuff to read out there, and I would actually keep that in mind far beyond Network Plus, because I've noticed a lot of times now when I put into Google a technical term that I need to learn something about, and I hit go, the second or third return, sometimes the first, is going to be a Wikipedia article. So I've actually gotten to the point where I go there straight there. Not one penny was paid for that endorsement. Now, let's take a look at some of these Ethernet standards and some of the values that I think you should know. Overall, 802.3, let me just move that for 1 second. 802.3 is the basic Ethernet definition. And as you can see, we've got a lot of sub-defs here, 0.3i, .3u, .3z, and we'll go over all of those in a moment. But 802.3 is the overall Ethernet standard. Now, some cert exams are still mentioning 10 base 2 and 10 base 5, and you really don't see those very often at all anymore. 10 base 2 is thin Ethernet or ThinNet. It runs at 10 meg, maximum range of a segment 185 meters, not a bad number to know. And I put in paren there 802.3a, that's what defines 10 base 2. 10 base 5 is thick Ethernet or thicknet, and the terms thin and thick there refer to the thickness of the coaxial cable that's used for these standards. And again, they're not things you really see in today's networks that often, but they're still out there somewhere. 10 base 5 runs 10 megasecond. Maximum range segment is 500 meters. Now we're getting into the substandards, or substandardizations, you want to put it that way. .3i defines 10 base T, which runs at 10 megasecond and has a maximum range of 100 meters. .3u is 100 base T, and that's 100 meg per second. That's fast. That's a fast Ethernet speed, 100 meg. .3z is a definition of gigabit Ethernet, and I put two different values, or actually two different expressions in the paren after gig Ethernet, but they're the same thing. 1,000 meg per second and 1 gig per second are the exact same thing. And I put it there because I want you to get used to it in the exam room, just giving it a few extra seconds anytime you see a speed, whether it's in a question or an answer. And just look at it a second and make sure you're not reading too fast, because the difference between 1 meg per second and 1 gig per second is pretty big. And of course, it could be kbps as well. So just watch those values, if you will. We actually have 10 gig Ethernet now, and that is officially 10,000 meg per second. Amazing. And it's .3ae that defines that. Wireless Ethernet we're going to discuss in another video, but 802.11 is your main wireless Ethernet standardization, or wireless LAN as it is sometimes expressed. I also put two non-Ethernet standards here, but I think they're good ones for you to know. 802.1, that's overall internetworking standards. That is not an Ethernet standard, but overall internetworking standards. And 802.2 defines the LLC sublayer of the data link layer. I also mentioned that in the OSI model video. But I wanted to put those here because this is a good reference list for you. I would know all of these. I would know every single one of them before walking into the exam room. Just a quick review of some of the high points of this particular section and one or two points that I just want to drive home one more time. And with CSMA CD, again, the entire process, the host listened to the wire before transmitting. That's a step a lot of people tend to forget, but actually that's the most important one. They're listening for another host already transmitting or any kind of signal that's already on the wire. And when collisions do occur, the sending hosts detect that. They're going to do two things. They're going to generate a jam signal telling the other host not to transmit. They will also invoke a random timer. And when that timer expires, they begin the entire process again by listening to the wire. That, again, is the part we tend to forget about. And we can avoid all this, and really we do in most of today's networks, by connecting each device to their own switch port. And when we're using a switch, and we place hosts in their own little collision domain by connecting them directly to a switch port, we greatly reduce the number of collisions, and we really make the entire network much more efficient because we've got fewer hosts waiting to transmit, we've got fewer hosts having to retransmit, we've got fewer hosts that are ready to transmit but can't because there's been a collision on the wire. It's just much more efficient for us to avoid the entire CSMA CD scenario and just get hosts connected to their own switch port. But again, the point I want to drive home here at the end, it sounds on the surface like having one collision domain is good and having multiple ones is bad, but it's quite the opposite. Having one big collision domain is what we want to avoid, and we create multiple collision domains by connecting the hosts to their own switch port. Just a little bit of a review here about broadcast domains, because we're in the same situation there, where with a broadcast domain, it sounds like, oh, well, you know, we'll have multiple broadcast domains, but that's bad. Well, no, that's actually good, because by default, all of our hosts connected to a switch are in the same broadcast domain. We saw that actually on the Cisco switch. And when one host sends a broadcast, all the other hosts are going to get a copy of it. But by placing the hosts into their own virtual LANs, and I mean not into their individual virtual LANs, but taking groups of related hosts and putting them into virtual LANs, we create smaller broadcast domains. And that lowers the chances greatly of a broadcast storm occurring. That's that snowball effect of broadcast that I talked about. And the problem is that this also prevents any inter-VLAN traffic, period. That's not good, but there are two solutions. Router on a stick, which is getting a router involved since we need a layer 3 device to have inter-VLAN traffic, and using a layer 3 switch, which is a relatively new technology. And the only other thing here I would put as far as the exam goes, like I said, anytime you see a list when you're preparing for an exam, it's a good idea to know it. I would know your Ethernet standards and speeds, and we will talk about that later again when we're discussing cables and cable speeds, that kind of thing. But those Ethernet standards I just had on the board a few minutes ago, I would know those very well. And that really sums up our discussion here of Ethernet behavior and standards and the use of VLANs. We're going to revisit switching here very shortly and look at some more details of switches. But for right now, we're all done, so I'll see you on the next video.